Hi everyone, welcome back. We're in the middle of section 2.3. We're talking about cont extensions. And when we left off, we had just shown some toy examples of cont extensions. We'd seen ways in which cont extensions capture the spirit behind limits and co-limits, as well as the toy example where we looked at the question of extending homomorphisms between groups, from subgroups to the whole groups. And those of you with some homological algebra background might remember that problem as being an important one in that setting, and this shows us one way in which cont extensions and their existence and non-existence sort of capture and generalize questions such as those. Now, the thing that I want to do in this video is give a theorem which tells us how to compute cont extensions under some mild assumptions. In other words, if I give you a functor and you want to actually find a cont extension associated to some pullback, then how can you write that down? And we saw when we were talking about limits that there's sort of a general procedure for how to think about them, at least, for example, in sets. And then from there, you might try to bootstrap your way to whatever your more complicated category is, maybe by UNITA, for example. We want to do something similar in this setting. We want a sort of recipe for how to construct cont extensions. And that's what we're going to do now, as well as give some consequences of this formula that will allow us to have more, shall we say, tangible examples, more concrete examples, less toyish and more sophisticated examples, if you will. So, to that extent, let's just get in and let's give a precise statement. So, as always, just recalling some notation, we have phi from I, oops, sorry, that should be the other way around if I want to be consistent with Kashiwara and Shapiro, also with my notes. Phi from j to I, some functor, and then we have beta, a functor from j to c. And now, I'll only write the theorem out for the one case, but the other case is sort of completely dual. So, we assume that we have the forward limit over all maps that are of this particular form. They go from phi of j to I, which we recall we have this notation ji for the slice of things that are indexed over I, beta j. We assume that this exists. This complicated limit is in C. And we remember that this means that the limit, we think of this as always existing in a suitable functor category, but really what we're saying is that it's representable. And we want this to exist in C for every I. Then phi dagger of beta exists, and we have a formula, which is that phi dagger of beta of I is isomorphic to the forward limit, phi j to I of beta j. And so in particular, if C has all small inductive limits, the forward limits, J is small, then phi dagger exists. And there's a sort of consequence that we'll get out of the proof, which is that if phi is fully faithful, then furthermore, so is phi dagger. And then, of course, there's a completely dual statement. I'm not going to write it out again, the whole thing again, but basically you just change dagger to double dagger. You change the forward limits to backwards limits. I'll just say dually, the corresponding statement holds for projective limits. Okay, so let's work on proving this. Oop, I didn't mean to highlight that. I didn't even know I could do that. So, proof. What we're going to do is propose that formula, basically. We're going to define phi dagger beta I to be this limit. I'm not going to continue to write the limit, with the 5s. You guys will just know until I tell you otherwise that that's what that will mean. And what we're going to do is basically check that this works. So suppose we have a morphism U, I to I prime. Then what we'll see is we need to define what this functor needs to do to morphisms, right? We're saying what it does to objects. We'll similarly define phi dagger of beta applied to U to be phi dagger beta I to phi dagger beta I prime using the limit. This is a thing that holds for every limit. And so now if we have any j with phi j going to I, then the pullback gives us a precomposition. So we can go phi j to I prime. And the universality of the limit then gets us a map from beta j to this forward limit to, we could call this beta j prime, which will be phi dagger beta I prime. Maybe I should be clear here. This is going to be phi, this will go from j prime to I prime. And so with this setup, we can pass to the limit, and this will give us a map we'll obtain the map we want, phi dagger beta u. Okay, so this is our setup for our functor. What we have to do now is actually check that this is an adjunction. So in particular, we need to show the isomorphism on the Hom sets. So let's see. What we're going to do for this is construct a pair of mutually inverse maps. So first, we'll have capital phi. This will go from JC this way, beta phi star alpha, to IC. And then here we have phi dagger beta alpha. So we define this map in stages. We define both of them in stages, but what we do is we take a U in here, and by pullback, we get a map which goes beta j to alpha j to alpha I. And this works for any I with phi j mapping to I. Maybe I write this down. For any I, phi j to I. And this gives us a morphism, phi dagger beta I. This is, of course, our forward limit. And this maps to our alpha I. But the catch to this construction is that this is a family of morphisms, and it's functorial in I. And so, as a consequence, this gives us a functor to this Hom, which is what we want. Now, we're going to construct a reverse map, and then we're going to have to check that these are mutually inverse to each other. So keep this in your brain for a moment. And now let's define a capital psi, which goes in the reverse direction. We have Hom IC, phi dagger beta alpha, to Hom JC beta phi star alpha, like so. Okay, so now suppose we have a V. That's the worst set inclusion ever. We have a V that lives in here. And this gives us a morphism, which is defined by taking phi dagger beta of phi of j to alpha phi of j. The former is by definition the limit, and for the sake of clarity, let me write this down. Phi j prime to phi j of beta j prime. And there's, by definition of this map, there's something, how do I say this? Because this is a limit, there is a map from beta j into this limit, because it's a limit. So putting the whole string together, we have this beta j, which maps into this limit, which maps to the alpha j. But this guy is, of course, just phi star of alpha j. So we just go all the way. Let me grab a color. We just go all the way as a composition. And this is our assignment. So we have to check that these are mutually inverse to each other. And this sort of took me a moment to think about. So maybe it's worth it for you guys to think about it also. But the idea is that the big phi associates to each map from beta to phi star alpha. We pass to the limit. The second map starts with these guys and associates to it the composition which factors through the limit. But we know that these are universal construction, so they're going to have to be mutually inverse to each other. Okay. Now let's think about this business of the fully faithfulness, and let's see how that falls out. So we assume further that phi is fully faithful. And we need C to have small inductive limits, whatever else I said. C is small, C has small inductive limits, and J is actually just small. Then we take some functor, beta, J, and let's say this maps into some category A, just a name. And then we have some J and J. Now we look at these slices. We have the category from JJ, J sub J, to J phi J. This is an equivalence of categories. By definition. And this tells us that if I look at phi upper star of phi dagger of beta J, well, what is this? This is the same thing as phi dagger of beta applied to phi j. But this is the same thing then as the limit, by what we just said, phi j prime to phi j of beta j prime, which is in turn the same thing as the limit from j of maps j prime to j, beta j prime, prime, which is of course just beta j. And the important bit here is this part. This step is the key, and this is where the fully faithfulness is used. Okay, and that proves in particular that our phi dagger is fully faithful also, which is what we wanted. Okay. I put the little box. Now, suppose we have alpha j to a functor from j to c, and then we have beta a functor j op to c. In this situation, we know that we have morphisms like so. We have the limit of alpha compose phi to the limit of alpha, and similarly for the reverse limit in beta. We saw this back in the section on limits and colimits. These give us morphisms like so, we have phi star of phi dagger to lim phi dagger alpha. And then similarly with the colimit, with the opposite functor, double dagger beta to lim phi op star. You just got to get this right. It's a bit of a mouthful. Phi dagger op beta. Okay, now if we apply this with the unit and co-unit, then we get some morphisms. Lim alpha to lim phi dagger alpha, and the colimit phi op dagger beta to lim phi op star phi op dagger beta. And I claim that when C has small inductive limits or projective limits, whichever one, and then alpha and beta are these as above, that these are isomorphisms. And this is sort of a corollary of what we've done. It'll be a short computation. What we do is we take x, we fix x in C, and we think about the constant functor, which I'll call k. And I'll mark an I to make it clear that it's a functor out of I to C, and it takes constant value x. This is, how do I say this? It's clear to see that if I try to pull back by some phi, and I look at this x at I, then that's the same thing up to isomorphism. Whoops, the j goes on top. Of the same constant functor, but now out of j. There's, I guess Kashiwara and Shapira call this an exercise, but this seems trivial to me. So maybe if one of you, if somebody can point out to me why this is non-trivial, then I'd be glad to see an elaboration on where the difficulty is, but this seems clear. So let's suppose for the moment that we take that as granted. And if we do, then we have the following computation. This Hom here is the same as Hom in the functor category of maps from alpha to the constant functor, which in turn is the same thing as the pullback to k. Instead of kj, it's now ki. And now we can apply the adjunction to get us in from Cj into Ci, and now we have phi dagger over here, phi kix. But this is the same thing as the limit phi dagger alpha x. And x is arbitrary, so we just apply the unit lemma to finish the proof. Okay, so this establishes for us our key formula, that we can compute Kohn extensions by taking limits over all of the suitable maps in the indexing category that map between the desired objects. And in this way, we can cook up, I don't know if I call this a formula or not, but a tangible way of getting a recipe for the examples. Off the bat, we see that, well, maybe I'll say this as a corollary, which is that adjunctions are cont extensions. So this is an exercise from Kashiwara and Shapira, but I'll state it and I'll give you an idea of how it works, which is that if phi is a functor with a right adjoint, so phi is the left adjoint, and we'll call the right adjoint psi, then phi dagger is the same thing as psi star, or is isomorphic to psi star, and psi double dagger is the same thing as phi star. And let's assume for the moment that we have the necessary completeness assumptions to make this easy to see. Then what happens is I take the limits over all the maps that run phi j to I. This has the same diagram shape as j to psi I. Because we know that we're dealing with this adjunction. And so this produces for us an isomorphism between the desired limit that we want and beta of psi of j. But the catch is that beta psi of j is, of course, just the same thing as psi star of beta of j. Well, yeah, okay, that's right. So that means we've got this isomorphism to phi dagger beta, which is what we would want to see. And of course, the argument is exactly the same in the reverse case, so I don't feel the need to elaborate on it. The important thing about this is that this immediately gives us many more examples. Because adjunctions are really common. For example, one we've seen many times is the forgetful free adjunction. Like, for example, between like a groups and sets. I could take a group and I could forget the group operation, or I could take the free group on the underlying set. That's an adjunction that we've seen before. Another one that we've seen a bunch of times is the tensor-Ham adjunction. I've been trying to make a concerted effort to call it the tensor-Ham adjunction because tensor is the left adjoint, so it should go on the left. Even though all my life until now I've called it Ham tensor. And there's a third example that's really important that I'm going to explain in the next video, because one of the things that I want out of this project is to learn a thing or two about homotopy theory, so I'm motivated to explore an example / exercise from Chapter 1's exercises, which has to do with simplicial sets. And the example is the geometric realization and singularization. And roughly speaking, what these do is, well, geometric realization sort of eats as its argument well, the way that I've seen it in the world of like simplicial complexes, which are sort of like simplicial sets, but I guess less general. What it does in that setting is it eats an abstract simplicial complex and it hands you a concrete topological space that lives in some Rn with that same combinatoric. So it's sort of a concretization, if you like. They call it a realization. I sort of disagree that it's geometric rather than topological, but that's a pedantic argument. The realization argument sort of accepts as its argument abstract complex and hands you something more tangible as its output, where singularization is sort of what it sounds like. It has to do with like singular homology. It accepts as its argument some complex, and then it tells you the maps from a simplex of a given dimension into the complex. And the claim is that these are also an adjoint pair, although that would require some explanation and a little bit of exploring what those things are all about, which is what we'll do in the next video. So hopefully it's not a problem that we're sort of dragging our feet in this section on cont extensions. The whole rest of this chapter, in chapter 2, seems to be about inductive limits in set. And I don't really know why, like, what the big deal is. I don't have enough. I guess I don't have enough experience to understand why we're doing all this we're doing quite yet. But in particular, this stuff about cont extensions is all very new to me. So I've been enjoying learning about all of this. But I'm sorry if in the meantime it sort of means that we're dragging our feet. But your patience is appreciated, and we'll continue to sort of make our way slowly through the chapter. Okay, this video is already almost a half an hour long, so I think I'll stop here, and I'll see you guys next time with this stuff on simplicial sets. See you then.